Welcome to my Abstract Algebra Exam 2 Review Problems and Solutions video. In this video we're going to go over definitions, theorems, calculations, and proofs related to intermediate group theory. That means we'll be looking at alternating groups, symmetric groups, cosets, Lagrange's theorem, homomorphisms, isomorphisms. We'll also prove something called the First Isomorphism Theorem at the very end of the video. And we'll also do calculations related to external direct products, for example, and look at some basic group classification problems. The first problem is about normal subgroups. Let G be a group and let H be a subgroup of G. It's going to be a special kind of subgroup called a normal subgroup. First, we want to state the definition, the original definition of what it means for H to be a normal subgroup of G. And then secondly, state the normal subgroup test, which is really a theorem to verify that the given subgroup is in fact a normal subgroup. So the definition starts this way. The same kind of thing that we have up here, let G be a group and let H be a subgroup of G. We say that H is normal in G if something extra happens, if something extra special happens, if AH, the left coset of H in G containing the element A, which I'll explain here in a second, equals HA, the right coset of H in G containing the element A, if that's true for all little a in G. Okay? What is this thing right there? That's, again, the left coset of H in G containing A. It is the set of all possible products of A times elements in H as H ranges over the subgroup capital H. And this thing, HA, is called the right coset of H in G containing A. It's the set of all products H times A, where A is now on the right, as little h varies over capital H. When those are equal, that's a special condition. It certainly happens if G happens to be an Abelian group, but in general, this special condition doesn't always happen. When it happens, that's a special kind of subgroup. We say H is normal in G, and notationally we also write H is not just a subgroup of G, but normal. We make this little triangle here to indicate that it's normal in G. That's the definition. And again, this stuff right here goes at the front of the definition. What is the normal subgroup test? That really is a theorem. Normal subgroup test. So this was part 1, and this is part 2 of this problem. We're once again going to let G be a group and let H be a subgroup of G. So that gets put down here as well. Then H is normal in G. I'll go ahead and use the symbolism again. If and only if, IFF stands for if and only if, XHX inverse is a subset of H for all X in G. Okay? Which actually ends up meaning it actually equals that, but it's sufficient to prove that it's just a subset. What is this expression? Sometimes called the conjugate of H in G by X. In general, it's not necessarily, well, okay, it's not necessarily going to be a set of H, but when that special case happens, then we say H is normal in G. This is a theorem, the normal subgroup test that can prove H is normal in G. What is this thing? It's the set of all products of the form X little h X inverse as little h varies over capital H. Okay? This is usually easier to verify than the definition, so it's worthwhile having a theorem. Problem 2 says, fully state Lagrange's theorem. And at least in the textbook that I use by Galligan, it is in 2 sentences. Lagrange's theorem is sometimes called the fundamental theorem of finite group theory. It's really, really important. It states that if G is a finite group, and H is a subgroup, not necessarily a normal subgroup, but any subgroup, H is a subgroup of G. That's notationally written like this, without a full triangle, make it look like a less than sign. H is a subgroup of G. Then the order of H, the number of elements in H, divides the order of G, the number of elements in G. In the book by Gallian, that's written the order of H like this divides the order of G, written like that. You could also write this with divides notation, but then there's lots of vertical lines like this. In some other books, instead of using these absolute value kinds of things for the order of the group or the subgroup, there's a little O used for the order. You could write O of G, O of H, excuse me, divides O of G. That's the first sentence of Lagrange's theorem. It gives you the possibilities for orders of subgroups. The second sentence of Lagrange's theorem says how many left cosets of H and G there are, which is also related to the concept of a factor group, also called a quotient group. Let's say it like this. Moreover, the number, all right, number like that, number of distinct left cosets, and also the number of distinct right cosets, because they'll be the same number, though they're not necessarily equal unless H happens to be normal, of H in G is equal to the order of G divided by the order of H. And again, if your book uses O notation, you could write that as O of G divided by O of H. And if you want to say a little extra here, Gallian does not do this, you could also say this is the same as the order of the factor group of G by H, also called the quotient group of G by H, whose elements, in fact, are left cosets. Okay? My students, in Gallian's book, in chapter 7, you don't have to write this last thing here. You can stop right there. Okay? That's the number of distinct left cosets and also right cosets. In problem 3, we are essentially using Lagrange's theorem for a fairly trivial application. Let G be a group whose order is 42. List the possible orders, not guaranteed orders, of subgroups of G. The converse of Lagrange's theorem is false. Just because the order of some number divides the order of G doesn't mean there's some subgroup of that order. And we're going to actually look at an example that illustrates that that's false later on. So it only gives you possible orders. We need to know the factors of 42, whose prime factorization is 2 times 3 times 7. What are those factors of 42? Well, don't forget the trivial ones like 1 and 42. In fact, I think I'll group these vertically. 1 and 42, 2 and 21, 3 and 14. What comes next? How about 6 and 7? And that will be it. There are no other factors of 42. And so this is the answer. These are the possible orders of subgroups of G, because those are all the divisors, positive divisors, and by Lagrange's theorem. Right? Again, it doesn't guarantee that for any one of these, except the trivial ones in 1 and 42, that there will be a subgroup of that order. There is definitely always a subgroup of order 1, the trivial subgroup, just containing the identity element, often called E. And there is always a subgroup whose order equals the order of the entire group, the group itself, the entire group itself. Number 4, about isomorphism. Decide whether U10 and U12 are isomorphic or not. That's supposed to be an or there. Or not. Briefly explain your answer. Okay? So what is an isomorphism? An isomorphism between two groups, from one group to another, is a one-to-one and onto function that is also what's called operation preserving. And in a nutshell, what that means is these two groups, if they're going to be isomorphic, will be indistinguishable from each other as far as their group properties go. Their Cayley tables can be put in correspondence with each other. In particular, that means they have the same number of elements. It also implies more. For example, there are the same number of elements of order 2, if there are any elements of order 2 in these, of order 4, for example, if there are any elements of order 4, etc. U10 is the group of units modulo 10, meaning the positive integers less than 10 that are relatively prime to 10, 1, 3, 7, and 9, under multiplication mod 10. U12 is the group of units whose elements are relatively prime to 12, positive integers relatively prime to 12 under multiplication mod 12. Its elements would be 1, 5, 7, and 11. They have the same number of elements. They both have 4 elements. It doesn't matter that the operations are different, and it doesn't matter that the elements are different. They still could be isomorphic. However, if you test out the orders of these elements, and maybe test whether one of these groups is cyclic or not, you will end up seeing they are not the same. They are not isomorphic. That is going to be the answer. Let's go ahead and figure out the orders of these things. 1, of course, in both groups is the identity and has order 1. 3 in U10, what is its order? Well, it's not 2 because 3 squared is 9, which is not the identity in U10. By Lagrange's theorem, that must mean 3 has order 4. This is going to be a cyclic group right here. 3 cubed is 27, mod 10 is 7, also not equal to 1. 3 to the 4th must be back to the identity. 3 to the 4th in ordinary arithmetic is 81, but then mod by 10 you get 1, the identity. Yes, 3 has order 4 in U10. You get funny looking equations like this. That's not the absolute value of 3, that's the order of 3 as an element in U10. And that means U10 is cyclic, and 3 is a generator of U10. I could write this. Another generator of U10 would be 7, for example. 7 would end up having order 4 as well. Yeah, and 9, 1 has order 1. 9 would have order 2. 9 squared is 81. 81 mod 10 is 1. The order of 9 is order 2. But this is enough to say U10 is cyclic. Evidently, U12 is not cyclic. 1 certainly has order 1. What about 5? 5 squared is 25. Mod 12 is 1. 5 has order 2. What about 7? 7 squared is 49. Mod 12 is also 1. Right away, you can now say these groups are not isomorphic. Both 5 and 7 have order 2, but only 9 has order 2 in U10. Just for extra emphasis, 11 squared is 121. 121 mod 12 is 1. All these elements, non-identity elements, have order 2 in U12. And that means U12 is not cyclic. So there's various reasons you could give here. You could say, no, for example, U10 is cyclic, but U12 is not. You could also say U10 has just one element of order 2. Again, that's the element 9. Whereas U12 has 3 elements of order 2. That's also enough to say they're not isomorphic. Okay? Various kinds of reasons you could give. That's the simplest thing to do in this case. On to the second page. How many elements of order 4 does this external direct product Z2 O plus Z4 have? By the way, with external direct products, not every book and or professor uses this plus sign with an O around it, called O plus. Sometimes they'll use a cross, a time symbol, for an external direct product. But in Galilean's book, this is what they use. As a set, this is the set of all ordered pairs, A comma B, where the first component, or coordinate if you prefer, of the ordered pair is from the first factor there in the external direct product. And the second component, or coordinate, is from the second factor in the external direct product. And since there are 2 choices for A, either 0 or 1, and 4 choices for B, either 0, 1, 2, or 3, the group operation for each factor here is addition, mod 2 in the first case and mod 4 in the second case. There are altogether 8 elements in this group. The order of the group Z2 external direct product with Z4 is 2 times 4 is 8. So there are at most 8 elements of order 4. And in fact, any element, of course, generates a cyclic subgroup generated by that element. And by Lagrange's theorem, that's going to mean the only possible orders of elements in here are the divisors of 8, 1, 2, 4, and 8. Turns out because 2 and 4 are not relatively prime, that this external direct product is not isomorphic to Z8, the cyclic group of order 8. So there will be no elements of order 8. This is all extra stuff I'm telling you. Come back here to the question at hand. We're after elements of order 4. The other fact that you need is that the order of an element in an external direct product, this ordered pair, is the least common multiple when you're dealing with finite groups of the order of the first component and the order of the second component. We want that for this problem to equal 4. We want to choose A and B so that that happens. A is either 0 or 1 and has order either 1 or 2. And B is either 0, 1, 2, or 3 and has order either 1, 2, or 4. So we want this LCM to be 4. There's only 2 possible ways that can happen. That implies either the order of A is 1 and the order of B is 4, or the order of A is 2 and the order of B is 4 again. There's only one way to choose an element from Z2 of order 1, make it be the identity, 0 in this case. Again, the operation is addition, mod 2 for the first factor. And there's 2 ways to make elements of order 4 from Z4. The elements 1 and 3 have order 4 under addition mod 4. In the second case here, the order of A is 2. That means A is the element 1. Again, the operation is addition here, not multiplication. 1 plus 1. 1 is not 0 in Z2, but 1 plus 1 is 0. 1 has order 2 in Z2. Once again, B would have to be 1 or 3. In each case, there are 2 possibilities. 2 possibilities. 2 possibilities. In total, giving 4 elements. 2 plus 2 equals 4 elements of order 4. Okay? All together. And you can even list them out. 0, 0, 0, 1, 0, 3, 1, 1, and 1, 3 would be the 4 elements of order 4 in this external direct product. Number 6. Let H and K be subgroups of G. G is a group. Order of H is 8, order of K is 12, and the order of their intersection is 2. It is a general fact, as an extra comment here, that when H and K are subgroups of G, that their intersection will also be a subgroup of G. The question is, how many elements are in this set, HK, which equals the set of all products little h times little k, as little h ranges over the subgroup capital H and little k ranges over the subgroup capital K. Notice I called this a set. In general, HK, this set, is not a subgroup of G. It will be if H and K happen to be normal subgroups, for example, but in general it's not. Show the necessary calculation to get the final answer for how many elements are in this set. You could call it the order of the set, but could be confusing because, again, it's not necessarily a subgroup. For my students, when I give this kind of problem, I'm expecting they know this from a fact in Gallien's book that we do talk about. The order of this set, the number of elements in this set, turns out to equal, through a proof that's about a paragraph long, the order of the subgroup H times the order of the subgroup K, I could put a dot in there for times, divided by the order of their intersection, H intersect K. Okay, that's a fact that can be proved. It's true even if HK is not a subgroup of G. It's true even if H and K themselves are not normal subgroups of G. We are assuming finite answers here, and we're given that the order of H is 8, and the order of K is 12, and the order of H intersect K is 2. So this ends up being ultimately 8 divided by 2 is 4, 4 times 12 is 48, and that is the answer for the number of elements in this set, which again, in general is not a subgroup, but could be if, for example, H and K are normal subgroups of G. It will be in that case. Number 7 is a long description of something going on here, but it's actually a fairly short problem as far as what is needed to be done. But it's worth reading through and thinking about based on things you should have learned if you're at this point in an abstract algebra class. Given a group G and a normal subgroup H of G, like I said before, written that way, we have defined the factor group, also called quotient group. In some books, Gallien's book uses factor group, of G by H, sometimes said G mod H, but it's not modular arithmetic, as follows. As a set, the elements are the left cosets of H and G. These expressions of the form AH, which by definition is the set of all products of little a times little h, where little h ranges over capital H, those are the elements of the factor group. You could write this. The group operation is coset multiplication defined by this product. The goal of this problem is to see why this is true. Or why this is why this is called well-defined. Well-defined right there. In the proof that this factor group is a group, the hardest part is to show that this coset multiplication, AH times BH, the left coset of H and G containing A times the left coset of H and G containing B, is this coset AB times H, the left coset of H and G containing AB. Why is that an issue? What do you mean by well-defined? I mean, if you used different coset representatives, would you get the same answer? AH could equal, for example, A prime times H, where A prime is different than A. Okay, that could happen, or it won't necessarily. A and A prime in that case would be representatives for the same coset of H and G. Do we get the same answer in the end? If I assume this is true and this is true, does it follow that this is true? If it is, then this operation is well defined. If I've got different coset representatives here and here, do I get the same coset in the end? That's a big issue. Below is a string of equalities that proves that the operation is well defined, just as equalities without explanations. Also based on the fact that if AH equals A prime H and BH equals B prime H, then you can say there's elements little h1 and little h2 of capital H, so that A prime equals A times h1 and B prime equals B times h2. That's something to know about when cosets are equal. Why does it work? Well, for example, with the first one here, A certainly, well, okay, think of it this way. We're looking at this equation here. A prime is certainly an element of A prime H because E is an H. H is a subgroup of G. The identity element E is an H. A prime is certainly in A prime H since A prime equals A prime times E. But we're saying A prime H, that left coset, equals AH, this left coset. And that would mean A prime also equals little a times something else in H. In other words, A prime equals A prime E also equals A times some other element of H. And you could say something similar between B prime and B. Your task is to identify, circle the two places where the string of inequalities here, where the normality of H and G is used. H does need to be a normal subgroup of G. Okay, that's necessary for this to work. So let's look at these equalities. Cosets. A prime B prime H. How do I go from here to here? I'm just using that property and this property. I'm replacing A prime by AH1 and B prime by BH2. So that's not using the normality. It's using the equality, the assumed equality of these cosets. Next step. AH1 BH2 capital H equals AH1 BH. What am I doing there? I am really letting the H2 go away. How? Because it gets sucked into H. H2 H would equal H. Once again, for a similar kind of reason as up here. H2 does equal H2 times E. That allows it to get sucked in, so to speak. Now I've got AH1B times capital H equals AH1B capital HB. I switched the left coset to a right coset? Well, kind of. It's like I got a combination of left and right cosets here. This is justified, it turns out. The BH got switched to an HB. Think back to the previous page in the definition of normality. That was the definition of the normality. There's one spot where it's used. Okay, put a big star there. Move from here to here, what happened? The H1 goes away, it got sucked into H. And here to here, I switch around the HB and the BH, excuse me. Once again, there is where normality is being used again. BH equals HB, and HB right here equals BH. Those are the two spots. I'm mimicking Galilean's proof here. I'm doing it on a coset level, this proof of the multiplication being well defined. You can also do this at a more element level. I'll leave that as an exercise for you. Bunch of true-false questions before we move on to some calculations. This is based on some knowledge. True or false? A finite abelian group G whose order is 147 has an element of order 7. First of all, we should probably double check and see if Lagrange's theorem might be violated here. An element of order 7 is going to generate a subgroup of order 7. How do you factor 147? Is 7 a divisor? 7 is a divisor. It's 7 times 21, in fact. Ultimately, it's 3 times 7 squared. 7 is a divisor, and here's the key. 7 is also prime. There's a theorem called Cauchy's theorem. Since 7 divides 147 and 7 is prime, that would say, yes, it does have an element of order 7, and it would also have a subgroup, a cyclic subgroup of order 7. Okay? Cauchy's theorem, to this point in intermediate group theory, requires the assumption that the group is abelian in order to prove it early in the book. Cauchy's theorem actually can be generalized to non-abelian finite groups. It still is true, but the proof is harder. Okay? I'll just put not necessary in general. That word's supposed to be necessary. But earlier in the book, in Galilean's book, you need that assumption if you're going to prove it more easily. But Cauchy's theorem does apply to non-abelian finite groups. It's true in either case. You got a prime that divides the order of the order of the group. There's going to be an element of that order and also a cyclic subgroup of that order. More factual knowledge. If G is a group whose order is 26, then G is isomorphic to Z26. 26 is 2 times 13. There's a theorem about classifying groups of order 2p where p is a prime bigger than 2. And the answer is false. It's not going to be necessarily cyclic. But there are only two possibilities up to isomorphism. Either that the group is cyclic like Z26 in this case, or that the group is isomorphic to dp, in this case D13, the dihedral group of order 26, which corresponds to what would be symmetries of a regular 13gon, which are rotations and reflections. I'm not going to try drawing anything there. The theorem says it's going to be isomorphic to one of those when your order is 2 times a prime, where p here, the prime, is bigger than 2. So that's false. 10. If p is a prime and the order of G is P, then G is isomorphic to dP, the dihedral group of order 2p. That's definitely false. If I had ZP there instead of dP, then it would actually be true. Up to isomorphism, if the order of G is prime, it's got to be cyclic. It's got to be isomorphic to ZP, the integers from 0 to p minus 1 under addition mod p, though the operation of G itself might not be addition. 11. So this would be true if I had a ZP there instead of a dP. 11. If G is a non-Abelian group, then this factor group of G by its center is not cyclic. This is something just to factually know this is true. It turns out there's something called the GZ theorem, which is a theorem, so it's also true, which is essentially this exact same thing except as it's contrapositive. It says if G mod ZG, the factor group of G by its center, which is the set of all elements in G that commute with everything in G, is cyclic, then G is abelian. Abelian, that's what I'm trying to write there. And the statement in number 11 is the contrapositive of that. If G is non-abelian, then this factor group is not cyclic. And so if this is true, then this is true as well. It's kind of an interesting little theorem. If this factor group is cyclic, then G is abelian, but that would actually imply more. That would imply that the center is the entire group, and it would also imply that the factor group must be trivial. Factor groups like this are never non-trivial cyclic groups. Trivial meaning just one element, and that one element is the generator. So kind of a weird thing that way, but this is still true. 12 is also related to the idea of a contrapositive. If G and G bar are groups and the group of automorphisms of G is not isomorphic to the group of automorphisms of G bar, then G is not isomorphic to G bar. That's the contrapositive of the statement, the implication that if G is isomorphic to G bar, then aught G is isomorphic to aught G bar. That is an easier implication to prove. Since this one's the contrapositive of this one, and I've proved that one, this one is true as well because a contrapositive means the same thing. And what this ultimately means is aught, sometimes called a functor, is an invariant for group isomorphisms. If you've got two isomorphic groups, their groups of automorphisms are isomorphic. So more usefully, if the groups of automorphisms are not isomorphic, then the original groups are also not isomorphic. More knowledge here. 13, aught of Z8, the group of automorphisms of Z8. By the way, automorphisms are isomorphisms from the group to itself, and so the elements of this are isomorphisms of Z8 to Z8. And the group operation is function composition. This is isomorphic to U8. And so now the question is U8 cyclic? Okay, that's just a fact to know. Well, U8 has 4 elements, 1, 3, 5, and 7. Positive integers less than 8 that are relatively prime to 8. Is this cyclic? You could just do a brief computations. 3 squared is 9, mod 8 is 1. So 3 has order 2. 5 squared is 25, mod 8 is 1. Yeah, this can't be cyclic. This is going to be false. 7 squared is 49, mod 8 is also 1. 3, 5, and 7 all have order 2. No element has order 4. This is not cyclic, therefore this is not cyclic because it's isomorphic to this. The answer is false. 14, the external direct product of Z2 and Z5 is cyclic. That's true. 2 and 5 are relatively prime. I talked about that briefly back up here. That I mentioned that this is not going to be cyclic because 2 and 4 are not relatively prime. I'm not going to bother coming up with the generator. This would have 10 elements in it. And that would also mean it turns out 4 generators, but I'll let you figure that out if you want. 8 and 14 are not relatively prime, so this one's false. On to page 3. Recall that Z of D6, the center of D6, the dihedral group of order 12, which would be symmetries of a regular hexagon consists of R0, which is the identity, rotate by 0 degrees, and R180, rotation by 180 degrees, is going to be a symmetry of a regular hexagon. D6 itself has 12 elements, 6 rotations, if you think of R0 as being a rotation, and 6 reflections, reflecting about lines of symmetry. Question is, what is the order of the element R60 Z6? This is a left coset. A left coset. R60 is an element in D6. ZD6, that's the center, is a subgroup of D6. What's the order of that element as an element of the factor group of D6 by its center? It's not 1. This is not the identity because R60 is not in the center. Hopefully pretty quickly you can see the answer has got to be 3. R60 ZD6 squared, by the definition of coset multiplication from the previous page, talking about the group operation and the factor group being well defined, you've got to multiply the representative times itself, or in this case compose it with itself. And R60 composed with itself is R120. R120 is also not in ZD6. This is not the identity element of this factor group. But if you cube the original element here, compose it with itself with 3 factors, so to speak, you are going to get back to the identity, because R60 cubed would be R180, and R180 is an element of the center. This does equal ZD6, which is the identity element of the factor group. Therefore, the order that we are after is 3. 3 is the smallest positive integer, such that when you raise this element to that power, you get back to the identity element of the group. 17, list all the possible Abelian groups up to isomorphism of order 27. In addition, for each of these groups, determine the number of elements of order 3. Okay. This is a classification theorem related to finite Abelian groups. Z27, cyclic group of order 27, certainly is one answer. Elements are 0 through 26. Group operation is addition mod 27. An example of a generator is the number 1. The group operation is addition, mod 27. That's cyclic, that's one answer. Turns out this external direct product is another answer up to isomorphism. And since 3 and 9 are not relatively prime, it's not isomorphic to Z27. This is not cyclic. But it does have 27 elements. And the final answer, if you think about the factorizations of 27 in terms of products powers of 3, 27 is 3 times 9. It's also 3 times 3 times 3. The last possibility is the external direct product of Z3 with itself with 3 factors. Number of elements of order 3 in Z27, what's that going to be? Well, it is a cyclic group. You could refer to the fundamental theorem of cyclic groups, of finite cyclic groups. It's going to have one subgroup of each order that divides the order of the entire group, 27 here. And that means there's going to be one subgroup of order 3. The converse of Lagrange's theorem does apply to cyclic groups, finite cyclic groups. One subgroup of order 3, and subgroups of order 3 have 2 generators. So there's going to be 2 elements of order 3. What are they? 9 and 18, if you think about it. 9 plus 9 is 18, not equal to 0 mod 27. 9 plus 9 plus 9 is 27, which does equal 0 mod 27. 18 plus 18 is 36, mod 27 is 9. 18 plus 18 plus 18 is 57. No, excuse me, 54. Mod 27 is 0. The identity element is 0. So there's two elements of order 3 in Z27. How about in here? It's good to think about the fact that the order of an ordered pair is, once again, the least common multiple of the orders of the components. And we want that to equal 3. How can that happen? It can happen if the order of A is 1 and the order of B is 3. It could happen if the order of A is 3 and the order of B is 1. And it could happen if the order of A and B are both 3. Now, B can also have order 9, but we're not thinking about that. In each case, there are two elements that fit these equations. 2, 2, 2, giving us a total of 6 elements of order 3. What's one example? If I think of this case, one example would be, for example, A is in Z3, it could be 1 or 2. B is in Z9, has order 3, it could be 3 or 6. So one example would be, for example, 1, 6. 1, 3, 2, 6, those are all examples that fit this. But overall, there are 6 elements of order 3. How about this one? Now we are talking about ordered triples for elements. The order of that ordered triple, or the group operation is defined component-wise, I forgot to emphasize that before, is the least common multiple of the orders of their groups, of the elements, excuse me, in the components. And I want that to equal 3. And actually, that's always going to be the case, except when A, B, and C have order 1. A, B, and C all have to either have order 1 or 3. And the only way this will not equal 3 is when these all have order 1, when they're all zeros. In other words, all of the non-identity elements in here have order 3. The answer is, for the number of elements of order 3, is 27 minus 1 is 26. Okay, but you also can think about this and think about cases like we did up here as well. Number 18. Let G be a group with order 21. If G has only one subgroup of order 3 and only one subgroup of order 7, prove our first proof. Prove that G is cyclic. Okay, so let's go ahead and write a careful proof of this in sentences. Let's think intuitively first. You could say let H be the unique subgroup of order 3 and K be the unique subgroup of order 7. By Lagrange's theorem, the only possible orders of subgroups are 1, 3, 7, and 21. Are there any elements of order 21? I hope it's pretty clear that there should be. Just take anything that's not in H and not in K. And it would have to have order 21 because it would generate a subgroup of order 3 or 7 or 21, but H and K use up all the elements of orders 3 and 7. That's the intuition. So let's see here. How should we write this as a proof? So here's our proof. Let H be the unique subgroup of order 3 and K be the unique subgroup of order 7. Since, let's see, the order of G is 21, the order of H is 3, and the order of K is 7, there would exist an element of G, call it A, such that A is not in H or K. It's not in their union. Now, be careful. H union K is not necessarily a subgroup of G. but as an element in a set, it's not necessarily in, it's not going to be in their union. We can find some element that's not in their union. There are, what would it be here? 21 minus, elements of order 3 in H are 2 of them, 2 generators, cyclic subgroup of order 3, 3 is prime. There would be 6 elements of order 7 in K. And we also want to subtract off the identity element. 21 minus 9, or 12 elements in G, but not in this union. You could write in G set minus H union K. 12 elements to choose from, but I only have to choose one of them. By Lagrange's theorem, the order of A, which is the same as the order of the cyclic subgroup generated by A, divides 21, so the order of A is 1, 3, 7, or 21. But by uniqueness of H and K, uniqueness, A could not have order 3 or 7, because then it would generate a cyclic subgroup of order 3 or 7, and that would have to either be H or K, but A is not in H or K. A is also not the identity element. By elimination, you could say, what we've already said, the order of A must then be 21, and done. QED. This would also prove there is a subgroup of order 21, and that means G is cyclic. I guess I forgot the final conclusion. I should say, therefore, G is generated by A, so G is cyclic. I forgot what the final conclusion was there. Excuse me. Okay. Let's move on. Here we come to our promised verification that the converse of Lagrange's theorem is false. A long-looking problem, but it's actually fairly easy when you go through it. Let's just fill in the blank. The group A4, alternating group. We haven't talked about the alternating group or symmetric group yet. S4 would be called the symmetric group of order 4, which has 4 factorial or 24 elements. It's excuse me, all the permutations on the set 1, 2, 3, 4. A4 is a subgroup of S4. It's got 4 factorial divided by 2, or 12 elements. It's all the even permutations in S4. Not going into a ton of detail about what permutations are. I'm assuming you've dealt with them, and look at the proof. We are dealing with them in cycle notation. It can be used to prove that the converse of Lagrange's theorem is false. In particular, A4, which has order 12, has no subgroup of order 6, despite the fact that 6 divides 12. Below are steps to prove this fact. Your task is to fill in the blanks. Okay? All right, let's go through it here. Prove that A4 has no subgroup order 6. First, note that any 3 cycle A, B, C, where A, B, and C are all numbers 1, 2, 3, or 4. I'm not thinking of this as being a group. I'm just thinking of it as being a set, and elements, like 3 cycles like this, permute these numbers. They're one-to-one and onto functions from this set to itself. This notation means A maps to B, B maps to C, and C maps back to A. I'm assuming you know that, where A, B, and C are all distinct numbers from this set. I should emphasize they are all distinct. This is in A4 because we can write it like that. It's in A4. As a product of two cycles, and because it's an even number of 2 cycles, that's why it's an even permutation, despite the fact that it's, as a cycle, it's an odd cycle. It's an even permutation because you can write it as an even number of 2 cycles. What does this mean? These are functions, remember? And you work from right to left. This one says A maps to B, but then this one says B maps to itself. So ultimately in the composition, right to left, A maps to B, which this notation means. How about B? This first permutation maps B to A, then this one maps A to C. So ultimately B gets mapped to C. With C, this one keeps it fixed, maps C to itself. This one maps C to A, so ultimately C gets mapped back to A. That's a factorization of this 3 cycle into the product of an even number of 2 cycles, and that's why 3 cycles are even permutations. And that's what the answer to this is. When you write permutations in cycle notation, there are various ways to write the same permutation. All 3 of these things mean the same thing. A maps to B, whether you think of it here, or here, or here. B maps to C, like that, or like this, or like that. And C maps to A. C maps to A over here by going backwards, maps to A here like that, and maps to A here like that. Each 3 cycles has 3 ways of representing them. And because of that, how many 3 cycles are there? The number of 3 cycles is 4 times 3 times 2, because there's 4 choices for A, 3 choices for B, and 2 choices for C from this set. But you got to divide that by 3, because for each 3 cycles there's 3 ways of doing it, and that does equal 8. And so A4 has 8 elements of order 3. 3 cycles have order 3. They're even permutations, but they have order 3. Each of these has order 3. The order of such a permutation is 3. You got to cube this thing to get back to the identity. Here's our argument now. Suppose to the contrary, it's an argument by contradiction, that there exists a subgroup H of A4 with order 6. We've got to get a contradiction out of this. We claim that H contains all the elements of order 3. And since there's 8 of them, 8 elements of order 3, that'll contradict the assumption that H has order 6. And we'll be done. To prove this claim, let A be an arbitrary element of order 3. Don't get confused with the A here. Maybe I should have used a different letter like alpha. It's not the same as an A from this set. A here is a permutation. For example, a 3 cycle. Arbitrary element of order 3. What I'm trying to show is that it's an H. If I assume for sake of contradiction that it's not an H, I must have to get a contradiction. Then H and the left coset of H and A in G containing A are distinct. It's a property of cosets. If A is not in H, these must be distinct. And their intersection is, moreover, their intersection is empty. Property of cosets. And the index of A4 in H, I forgot to use index notation when I did Lagrange's theorem, I think. I wanted to, but I forgot to. In other words, the number of left cosets of H in A4 by Lagrange's theorem is 2, 12 divided by 6. And that'll mean A4 can be written as H union AH. I guess I'm not really using the fact that A is not in H to say that, but I am using this fact here. Trying to get a contradiction. Consider A squared. By the conclusion of the preceding paragraph, we know either A squared is in H or AH. H and AH form a partition of G, of A4. Their intersection is empty and their union is the entire thing. So any element in A4 has to be in one or the other. And actually you could even say not both. If A squared is in the first one, then by closure of H, if you square that, you'll also stay in H by closure, because H is a subgroup of A4. And since A has order 3, A to the 4th will equal A. That's where we use the fact that A has order 3. In other words, A is an H. But wait a minute, I assumed A was not an H. Up here. So we get a contradiction. If, on the other hand, a squared is not an h, but an AH, then a squared will equal a times little h for some little h in capital H. And you can cancel the a's and say, ultimately, a equals h. But that contradicts the fact that I'm assuming a is not an h. So it's kind of convoluted, it seems, but it really is accurate, a valid argument. Therefore, since the claim is proven and H, a subgroup of order 6, contains all elements of order 3, that's absurd. No such subgroup can exist. 20. Symmetric group. Let G be S6. Symmetric group of order 6, which really has 6 factorial or 720 elements. Part A, find the number of elements of order G in G of order 6 that are 6 cycles. 6 cycles would have the form A, B, C, D, E, F, where these numbers are all distinct and they're from the set 1, 2, 3, 4, 5, 6. A gets mapped to B, B gets mapped to C, C gets mapped to D, D gets mapped to E, E gets mapped to F, and F gets mapped back to A. 1 to 1 and on to functions from the set of numbers 1, 2, 3, 4, 5, 6 to itself. How do you figure out how many elements of this form there are? Well, there's 6 choices for A, 5 choices for B. They have to be all distinct. 4 choices for C, 3 choices for D, 2 choices for E, and 1 choice for F. But that's not the answer. That's the number of elements in S6. Since each one of these 6 cycles can be represented in 6 different ways, you got to divide this by 6. Instead of the A being first, I could have the B being first. Or I could have the C first, or the D, or the E, or the F. You've got 6 ways of doing each of those. So altogether, this is giving you 120 elements that are 6 cycles. And those 6 cycles would have order 6 as an element of the group. B, find the number of elements of G of order 6. Order 6 that are products of 2 disjoint cycles. And this is kind of tricky. We also want to remember that disjoint cycles commute with each other. I can put them either direction, compose them either direction. Disjoint cycles means in cycle notation they don't have any numbers in common. How are you going to get it to have order 6? When you multiply or compose 2 disjoint cycles, they're going to have order equal to the least common multiple of the orders of each cycle individually. It's not the same thing as the external direct product fact. We're talking about S6 here, no external direct product at all. So if I'm going to get order 6, one of them is going to have order 2 and one's going to have order 3. Say it looks like this. There's a 2 cycle, it's got order 2 as an element of S6. There's a 3 cycle, it's got order 3 as an element of S6. I'm composing these. The order of this is going to be 2 times 3, or the least common multiple of 2 and 3, which is 2 times 3, or 6. You got 6 choices for A, 5 choices for B. These numbers have to be different. You got 4 for C, 3 for D, and 2 for E. But we got to divide. There's 2 ways to write this 2 cycle here, either A first, then B, or B first, then A. So I got to divide by 2. There's also 3 ways to write a 3 cycle, either CDE, DEC, or ECD. Those all mean the same thing, so I got to divide by 3 as well. Do I need to divide by anything else? That may not be clear here. In fact, I need to think about it. It's a little tricky. If these cycles had the same length, if they were 2, 3 cycles, the order wouldn't be 6 anymore, but switching them around would not change the form of these things as a 2 cycle first and a 3 cycle as I have here. It would be indistinguishable is what I'm trying to say. If I switch these around, put the CDE over here and the AB over here, I have not created a new permutation because these are disjoint cycles, they commute. It would be the same permutation. So the upshot of what I'm trying to say is you do not need to, for example, divide by 2, because switching these around would not change anything. This is the answer, and it ultimately equals 6 times 5 times 4. 30 times 4 is 120. 120 elements of order 6 that are product of two disjoint cycles. Part C, using your answers from parts A and B, find the number of distinct cyclic subgroups of S6 of order 6. Cyclic subgroups of order 6 are generated by elements of order 6. And there's always two such elements for any given cyclic subgroup of order 6. That's something you should know with working with cyclic groups. First of all, the number of elements of order 6, it's got to be the sum of these two things. 120 plus 120 is 240. But we're after the number of distinct cyclic subgroups of S6 of order 6. For each element of order 6, it generates the cyclic subgroups of order 6, but any such cyclic subgroup has two generators, each of which has order 6. And so therefore, the answer to the number of cyclic subgroups of order 6 is 240 divided by 2, number of generators for any cyclic subgroup of order 6, 120 cyclic subgroups of order 6. So the answer to each part in this problem is the same, 120 in each case. By the way, S6 could have non-cyclic subgroups of order 6. There are, not every group of order 6 is cyclic. In fact, there are plenty of non-cyclic subgroups of order 6, and they're all isomorphic to S3. They're not equal to S3, but they're isomorphic to S3. I'll let you think about that. Also isomorphic to D3. Almost getting close here. 2 more pages. The very last page is a proof of the first isomorphism theorem. This page has got calculations with U groups. Here's a fact from chapter 8. Oh, I probably shouldn't have said that in this video. This is from Gallian's book. G is this U group of units. In this case, positive integers less than 64 that are relatively prime to 64 under multiplication mod 64. Multiplication, not addition. Use a fact from Gallian's chapter 8 to find positive integers m and n such that U64 is isomorphic to Zm external direct product with Zn. That's a memorization thing, okay? In general, U of 2 to the n is isomorphic to the external direct product of it's Z sub 2 to the n minus 2 with Z2, it turns out. That's a memorized fact. And this is true for all n greater than or equal to 2. Yeah. All integers n greater than or equal to 2. Therefore, in our case, n is 6. Therefore, U64, which is U2 to the 6th, is isomorphic to the external direct product of Z sub 2 to the 4th with Z2, which is not cyclic, because 16 and 2 are not relatively prime. That's just a fact to remember. Part B says, use your answer from part A to state how many elements G has. It's not so obvious thinking about U64, but once you think of it as isomorphic to this, you can say U64 has order equal to 16 times 2, 32. It's a non-cyclic group of order 32. C is G cyclic. No, just said it. Since Z16 external direct product with Z2 is not cyclic, because 16 and 2 are not relatively prime. The GCD of 16 and 2 is 2, which is not 1. They're not relatively prime. D, use your previous work to determine how many elements of order 16 that G has. Order 16. Element, I can think of in terms of Z6, this external direct product, and I can think in terms of this fact. I want this to equal 16. That's the want. How do I choose order of A and order of B? If I'm thinking of B as being from Z2, it's either 0, 1, and A as being from Z16. I could either have A has order 16 and B has order 1, or A has order 16 and B has order 2. For B, in each case, there's only one element. In this case, B is 0. In this case, B is 1. Under addition mod 2 in Z2. So the question is, how many choices are there for A? How many positive integers less than 16, in fact, are relatively prime to 16? Non-negative integers starting with 0. I want to think about the generators of Z16. 16 is 2 to the 4th. Generators of Z16 are going to be numbers less than 16, relatively prime to 16. That's going to be all the odd numbers. 1, 2, 3, 4, 5, 6, 7, 8 of them. So in each case, you get 8 elements, altogether giving you 8 plus 8, or 16 elements of order 16. In Z16, external direct product with Z2, so also in U64 because it's isomorphic to that. E, let H be this subgroup, the cyclic subgroup of G, which is U64. Sorry. You're trusting me that that is a subgroup, and in fact a normal subgroup, which it would have to be because G is abelian. Do calculations to find the order of 3H in the factor group. By Lagrange's theorem, let's see here. We can say the order of this factor group G by H is the order of G divided by the order of H, which is going to be 32 divided by, what's the order of H here? 1, 2, 3, 4, 5, 6, 7, 8. 32 divided by 8 is 4, and therefore the answer has got to be 1, 2, or 4. Now, 3H is not equal to H because 3 is not in H. 3H does not equal H since 3 is not in H, and what that means is 3H is not the identity element of the factor group. So 3H does not have order 1, not equal to 1. Does it have order 2? Square it. You get 9H. Is that H? Go back up here. 9 is not in H. And therefore, 3H does not have order 2. And you could then right away say by Lagrange's theorem it's got to have order 4. Since the factor group has order 4, and 1, 2, and 4 are the only divisors of 4. You could also verify it computationally. (3H cubed) is 27H is not equal to H because 27 is not in here. But 3H to the 4th is 81H. We do need to mod 81 by 64. That's the same as 17H. That does equal H because 17 is in H. we are back to the identity element of the factor group. That's another way to see, ultimately, that the order of 3H in the factor group is 4. 22, let phi be a homomorphism from U15, this group of order 8, to itself, whose kernel consists of the cyclic subgroup generated by 4 under multiplication mod 15. 4 squared 16 mod 15 is 1. That's a cyclic subgroup of order 2 in this group of order 8. If phi of 7 equals 7, find all elements of U15 that map to 7. Based on a fundamental fact about homomorphisms, the inverse image or preimage of any element is in the domain the left coset of the subgroup of the kernel. Now, in general, this is a little funny since 7 is getting mapped to itself. In general, what you've got here is if phi is mapping G to G bar, and you're looking at the inverse image or preimage of the element little g bar, the answer would be that it's the left coset of the kernel containing G where phi of G maps to G bar equals G bar. The G and the G bar are the same here. They're both 7. So it's a little weird that way. This is like the G bar here, and this is like the G. But phi of G equals G bar. But that is the answer, so what I need to do is figure out what that coset is. The kernel consists of 1 and 4. So this coset consists of 7, and 7 times 4 mod 15. 7 and 28 mod 15 is 13. And that would be the answer. Those are the elements in the domain that get mapped to 7. It's not a subgroup of U15. It's a left coset. That's the way homomorphisms and kernels relate in this context. Last problem is a proof of the first isomorphism theorem. Ideally, you'd write this in sentences, but for sake of time, I'm just going to give you the idea of the proof. Here's what it says. Let phi from G to G bar be a group homomorphism. I haven't said what homomorphism is. It's a mapping from one group to another that's operation preserving. Phi of G1 times G2 is phi of G1 times phi of G2. Isomorphisms are homomorphisms that are also one-to-one and onto. The goal is to prove that the mapping that I call phi bar, Galilean doesn't call it that, but I call it phi bar, from this factor group to the image of G under phi. This is the set of all outputs phi of little g as little g ranges over capital G. And it does not necessarily equal G bar. This is not necessarily onto. Defined by this formula is an isomorphism. Okay, there's 4 steps to do. Step 1, show this mapping is well defined. The well-defined issue came up earlier with factor group multiplication. It's coming up now in defining this proposed homomorphism, isomorphism in fact. Iso, so it's going to be not just operation preserving, but one-to-one and onto. Step 2 is to prove it's one-to-one. Step 3 is to show it's onto. Not G bar itself, but the image phi of G. If you assumed phi was onto to begin with, then this phi of G would equal G bar. And sometimes the first isomorphism theorem is stated assuming phi is onto. And 4, show it's operation preserving. So again, I'm just going to give you the ideas of these things, not full details. Step 1. Show it's well-defined. What did well-defined mean with factor groups? It meant if AH equaled A prime H and BH equaled B prime H, that you get the same answer when you multiply cosets. ABH equals A prime B prime H. To show this phi bar function is well defined, you're trying to show it's a function. If you had two representatives of the same coset, you get the same output. If you assume phi, let me call it G1 cur phi equals phi of G2 cur phi, what am I trying to show? Excuse me, that's the one-to-one. If I assume G1 cur phi equals G2 cur phi, does it prove that I get the same answer in the end? Phi bar of those things is the same thing. It should. That's what it means to be well defined. These are left cosets. To say they're equal is equivalent to implying, for example, that if I pretend I'm multiplying both sides of this on the left by G1 inverse, that this is true. These are properties of cosets, and that's equivalent. In fact, I'm going to go ahead and do steps 1 and 2 at the same time here. And I'll just explain them. The left to right direction is going to be step 1. The right to left direction is going to be step 2, that it's one-to-one. These are equivalent. They mean the same thing, so the implication goes both ways. And that's equivalent to G1 inverse G2 being an element of the kernel of phi. Now you could just jump from here to here. That's allowed. Okay, but I did this intermediate step. And what is that equivalent to? It's equivalent to phi mapping those things, that product, to the identity element of G bar. Call it E bar. By the fact that phi is operation preserving, phi is OP, that's really the key step, that's equivalent to phi of G1 inverse phi of G2 equals E bar. It's like the phi factors through, not literally, it's not a multiplication, but it's kind of like that. You can go from here to here. And you also can say, by the fact that phi is operation preserving, that phi of G1 inverse is phi of G1 inverse in G bar. What's my goal in all this? My goal is to get to showing this was well defined, and therefore phi of G1 equals phi of G2. And I'm almost there, because I just need to now multiply both sides of this equation on the left by phi of G1. And I'll get phi of G2 equals phi of G1, which is the same thing as phi of G1 equals phi of G2. So the left to right implications here, starting by assuming that you got two different representatives of the same coset, showing that you get the same answer in the end, is enough to say this is well defined, that it makes sense. The right to left implications are enough to show phi bar is one-to-one. I should maybe add one more step here. This means phi bar of G2 cur phi equals phi bar G1 cur phi. Go right to left for one-to-one. Assume phi bar of these inputs are the same, and try to show the inputs themselves are the same. And all these implications, all these things are equivalencies, two-way implications. We can go from right to left in each step. And that would prove phi is one-to-one. Step 3. Show phi is onto its image. By the way, after I finish this proof, I'm going to draw kind of a fun picture that people like to draw in this situation, so hang on for that. Show phi bar is onto its image. Well, phi is onto its image by definition, and that's going to imply phi bar is onto. Let little g bar be in this direct image of g under phi, which is a subgroup of G bar. We're trying to show there's something in the factor group that gets mapped to the given G bar, such that phi of G equals G bar here. Well, you just got to use the fact that phi is onto its image. Therefore, there exists a little g in capital G such that g bar equals phi of little g. That's what it means for that to be true. And that's the same g that you can use for this left coset here. Therefore, phi bar of g cur phi, by the formula for phi bar, right there, is phi of g, but that is g bar. Done. That's enough to say phi bar is onto. Not all of g bar, but onto the image of g under phi. If phi were itself were onto, that would equal g bar. Step 4. Show phi is operation preserving. Isomorphisms are homomorphisms. So give me two arbitrary left cosets. Like this. Multiply them and plug them into phi bar. Do I get phi bar of the first one times phi bar of the second one? That's analogous to this thing up here. Well, you just got to plug away. How do you multiply left cosets? You multiply their representatives. That's just coset multiplication. Now, the only thing you can do is just use the formula for phi bar. That's a lot of what you do in this class is just do the only thing you can do, but you got to know what you should do before you do it. Use the formula for phi bar. That's all you can do here. This formula here, using phi, applied to the coset representative. This equals phi of g1, g2. It's the definition of phi bar. But now, hey, I must have to use the fact that phi is assumed to be a homomorphism. Phi itself is assumed to be operation preserving. This is phi of g1, phi of g2. But hey, that's the same thing I'd get if I applied phi bar to the corresponding left cosets. And that means I'm done. That's the definition of phi bar. Once again. Okay? The diagram I want to make to close out the video is in this context. If you got G mapping to its image, which is a subgroup of some other group, G bar, the way people think about defining the map phi bar here with this formula, they think visually in terms like this. They imagine mapping G bar onto this factor group, which is what the domain of phi bar is. How? By taking an arbitrary element little g in capital G and mapping it to its left coset, the left coset of the kernel containing little g. This is sometimes called a projection mapping, sometimes labeled with the Greek letter pi, but that's not the number pi. It's a mapping symbol in this case. And they call phi bar the induced map, taking this element and mapping it to phi of g. And this diagram is said to commute. You draw 3 lines there to say the diagram commutes. And what that means is phi itself can be factored, so to speak, as the composition of phi bar with pi. Doesn't really prove much in and of itself, but it helps you understand how phi and phi bar are related. I think I got everything right here. Okay, and again, here was the statement of the first isomorphism theorem if you want to look at that again. Thanks for watching.